So basically, the question that we had at the beginning was, what is the difference between a tap changer and how to simulate a tap changer and a voltage regulator? The voltage regulator will be right along the feeder. You know, even that sometimes they show a voltage regulator at the substation. Why would you put a voltage regulator at a substation when the power transformer doesn't have a tap changer, right? Otherwise, you will be having two devices at the same place to regulate the voltage. So if you bought a power transformer with no tap changer, right, for whatever reason, right, and this could happen, for example. So most of the time you have a tap changer. This source is representing the ideal voltage source, right, your infinite bus, referred to the secondary side. So what you do is you calculate, your feeder is given, right, and you calculate your R and Ls, and here you calculate your R and L for the loads, and basically you run PSpice, and then remember that this is an AC source that you have to input the peak voltage per phase. Remember, this is one phase of your three-phase system. And then you calculate the voltages at each node, and you have a command, right, that allows that to do, right? You can either plot, and you can go and look at the peak, like some of you do, but then you can go into the command within probe, trace, right, at a trace, and you are going to have a command. Yeah, it seems that everything is okay. And so basically, what we have is that you run that software, and you're going to plot this. Basically, you're going to plot the voltage at all those nodes, and you should get a figure similar to your figure 9.1 in the textbook, right? That's what you're going to get, right? You're going to get a figure similar to 9.1 in the textbook. Now, what is the voltage at the end of the feeder? It has to be greater than 95%. If that voltage here at the end of the feeder is below 95%, what's happened? You do not have voltage regulation. You are not within the region, right, in table 1, which is called favorable zone, range A, right? If you go to table 1, there you have the favorable range, right? So if you are not there within the plus minus 5% here, what you do? Then you have to go and put shunt capacitors here. So what you do is, after you do the first pass, you look for the voltage at the end, at the last node, and if it's below 95%, you do not have voltage regulation. Then what you do is you look at the largest node, and then you are going to put shunt capacitors. And if you look at some of the slides that you have here, show you how to calculate the shunt capacitors. Now, this slide, right, if you are going to use a voltage regulator, and normally students tend to say, well, let me use a voltage regulator. And what they do is, and this is what I explained earlier, they tend to put a source here, right here. This is your infinite bus. Here you put another source. And let's make this source 10% greater. So you multiply the peak value by 10%, right? The problem is that now current flows from here to the left, and current flows to the left, and also to the right of this node, because you are putting a voltage source. What is a voltage source? It's your infinite bus. What is your infinite bus? It's a power source that can give me infinite current, and the voltage stays constant. So if you try to model a voltage regulator using a voltage source, it's the wrong. That's the reason why I have a cross here. The way that you model a voltage regulator, and in this case, is you use a transformer, right? You put a transformer from this point to this point, and then the secondary, right, you connect the rest of the feeder. Now, this is a challenge for most students using PSP, right? And in fact, there are several models, and then you tend to get. So the best way of solving, right, the homework is you run that, then you identify those buses where you have a large reactive power. Why you are not going to put a capacitor on every bus? Expensive, cost. 10 cents per kilowatt hour cost in Arkansas. If you talk any vendor of demand side management solutions, they are going to tell you, we don't try to sell them in Arkansas. Why? Because at 10 cents per kilowatt hour might as well pay. You know, so really there is no advantage. In Pennsylvania or California, where the cost of electricity is higher, all these demand-side management solutions that the vendors like S&C, Cooper Power sell, they basically have a quick return in the investment. So the way that you do this is, can I just use a tap changer here, 10%, and then I do not worry about putting capacity? And probably you can fix the problem, right? Probably you can fix it. Probably you're going to have that the last node will be 95%. What is the problem? The problem is that now here, what you have, real power and reactive power. And what is the problem? That the utility pays for Q. Your electric bill is kilowatt hour. Means you pay for the peak power. But the utility, when they go and they purchase, they have to pay an extra charge, a surcharge, for the Q. So that's the reason why you have to use capacitors first. And then after you use capacitor, if this node is still below 95%, you increase the voltage at the substation, mimicking a low tap changer. You might need to increase it by 5%, you need to increase it by 10%. That's the maximum. If you are buying a tap changer that is higher than plus minus 10%, what you are having is something that is not custom. And so here is basically how you model the loads at each. That's what you did for. So this is taking to the next level the homework that you did for chapter 5. So you need to go and correct the mistakes that you had in that PSPICE. I don't remember if the resistance and the inductance, if the feeder is the same. I may have changed the feeder, so you have to change those numbers. And that's basically what you're going to have, right? This is how you calculate R load. Since you are using the same voltage, right, they are in parallel. And here is, and you run that system in PSPICE. And this is material from chapter 8. By the way, these are loaded up in the website. And so what you have to do is, basically, at those nodes where you want to connect a capacitor, you know what P load is, here the three-phase power, and you know what is this. Right? So I know P load and Q load. Capacitors do not provide real. So basically, PS equal to PL, this is assuming just. So here, basically, all the power, if this is just one node, comes from the source. And then here, basically, if you want to compensate the power factor of this load, what you have, this is kind of Kirchhoff current law. You have Q source, right, the power here, the reactive power coming here. This is the node, right? And if you add here, Q source plus Q cap, right? They have the same direction, has to be equal to QL. Remember, these are complex numbers, complex power. So you add the real powers and you add the reactive power, and basically the direction tells you whether you have a sign or not, right? If I move QL to this point, what do I have? Minus QL equal to 0, right? That reminds me of Kirchhoff's current law that says that the sum of all the currents going into a node are equal to 0, right? And so, if I want unity power factor, QS is equal to, for this to be the load, obviously requires this, right? This is my electric motor. This is my building, right? The Baldor building, right? Where I do have certain reactive power demand. I cannot change that because that's what the load, that's what these lights require for that reactive power. So the goal is that the capacitor is going to provide the reactive power required by this. And so if I want unity power factor, then QS must be 0, right? That's what means unity power factor, right? That I don't have a QS component. And so QC from this equation is equal to QL. Now, QL doesn't change because the load needs this reactive power, right? Now, if you want different source power, right? Let's say I don't want unity, I want 0.96 lagging. You always want lagging. Then the Q source desired, right? That's what I want. I want the source to have a 0.96 lagging. It's going to be equal to P source, right, which is the load power, times the tangent, right, of, and this is the P of the load, right, times the tangent of the angle that I desire. So I have to get what is the angle corresponding to 0.96, right? And what you got here is basically where this is the watt, for example, for a motor, and here you have kVR lagging, and here you have kVR leading, and basically here it says Q cap is Q load, right, minus the Q source desired. And that's the amount of capacitors that